Hereby, I open the academic ceremony in which Maike-Elisa Ostheller will defend her academic thesis titled Melt-Electrospinning of Biobased Polybutylene Succinate from lab scale towards prototyping. Dear candidate, may I invite you to present a summary of your study and the conclusions of your thesis?
Yes. Okay. Dear Prorector, dear Assessment Committee, dear members of the Assessment Committee, dear colleagues, family and friends, I would like to welcome you to my PhD defense. The lady told me to enjoy the next 15 minutes, so let's just enjoy the next 15 minutes where I would like to guide you through the research of my thesis. But before we start and deep dive, let's have a look at the conventional medical face mask, something we all got to know during the corona pandemic. So such a face mask is a disposable medical product designed for the single use only. It consists out of 3 layers, so we have an outer layer, an inner layer, and a middle layer, the so-called filtration layer, which is the heart of such a medical face mask. All of them depend on fossil-based resources, since they are made from PP, and they are all made from microfibers. Unfortunately, often they end up in the environment, enhancing microplastics emission. On the other side, and contrary to those fossil-based resources, they are bio-based and biodegradable materials, which can be entirely made from bio-based and renewable resources. They can be designed in a way that they degrade under certain environmental conditions, and as innovative as those materials are, they might also offer innovative processing technologies. So now one might wonder if there would be a way of producing such a mask independent of fossil-based resources in order to prevent microplastic pollution, and by this also to allow the usage of innovative production technologies. So this being said, an example of an innovative material would be polybutylene succinate or PBS. PBS can be 100% made from renewable resources. It is an aliphatic polyester, which also leads us to one of its most important characteristics, which is its biodegradability. And as of now, it's already found in a diverse application area. Contrary, an innovative processing technology could be electrospinning. It has its origin in solution electrospinning, which requires toxic solvents in order to dissolve the polymer up front. However, it leads to the production of nanofibers. On the other side, there is the process called Melt-Electrospinning, which doesn't use any solvents because it's processing the melt. However, achieving nanofibers as of now is still challenging. But now one might wonder if PBS could be processed by Melt-Electrospinning and could eventually lead to nanofibers, which could be used as a filtration layer medical face mask to not only lead us to environmental benefits, but also to bring us some better characteristics. This being said, leads me to one of the major research questions of my thesis. So is it possible to produce a Melt-Electrospun filter for medical face masks from bio-based and biodegradable polybutylene succinate? And there were several sub-questions guiding me. So the first one is PBS favorable for the process? Do material modifications make sense? Do machine modifications enhance the process? And is it possible to transfer the findings from a lab scale to a pilot scale machine? Before we now deep dive into the results, let me quickly introduce you to my potato equation, because most of you might know that cooking is one of my favorite hobbies. And doing the research in the past 4 years and cooking have a lot in common for me, and I hope to prove that commonality within this presentation now. So let's assume in order to make mashed potato or fries, we take a main ingredient, which is the potato. We add ingredients like butter, milk, salt, pepper. We use a preparation method to, at the end, have our final dish. So let's assume the following. In order to prepare a filtration layer for medical face mask, we don't use potatoes, but we use PBS as the main ingredient. We add additives such as silver and curcumin, And our preparation method is the Melt-Electrospinning, which at the end hopefully leads us to, or brings us to our filtration layer. And since cooking is probably more familiar to most of you than Melt-Electrospinning, let's have a quick look at the general Melt-Electrospinning setup, which consists out of a spin pump. We have a syringe, which is filled with the polymer granules connected to a heating element. We have a nozzle, which is on the tip of the syringe. We have a collector, which is connected to a high voltage unit. And these parts are required for our Melt-Electrospinning setup. There are certain requirements that need to be fulfilled in order to have a non-woven sample at the end, which is the formation of a Taylor cone, and we need to have an interaction of the fiber with our electric field. So now the question is PBS favorable of the process? So remember, we are not talking about cooking or frying, but we are focusing on our Melt-Electrospinning technology. And after an intense analysis of the material and its resulting properties, I focused on the behavior of PBS under these process parameters. And a statistical analysis at the end proved that the electric field strength has the greatest influence on the final fiber diameter. And we achieved fibers in a range of 30 micrometers. So yes, we are very far away from nanofibers, but however, we can answer this question with a clear yes. PBS in general is favorable for the Melt-Electrospinning process. But there are two major drawbacks that hinder us from achieving nanoscale, which is on the one hand, the viscosity of the material, because other than water, for instance, the melt of a polymer is rather known to be high viscous, so which makes it very hard to stretch. Additionally, our polymers are not conductive, so we have a limited interaction in the electric field. And an approach to overcome this would be, for instance, the addition of additives. So other than when we prepare mashed potato and we add butter, we added different weight percentages of curcumin and silver. And we did not only study the effect on the viscosity and the conductivity, but also on the thermal behavior, on the degradation, on the diameter, and also on the antibacterial efficiency, since curcumin and silver are both known to be highly effective against bacteria. And at the end, both additives not only reduce the viscosity and increase the conductivity, we also realized a significant reduction in fiber diameter. So yes, material modifications do make sense. However, out of the machine perspective, there are also certain parameters or parts that allow optimization. And since we know that the electric field strength has the greatest influence on the final fiber diameter, one might wonder if an optimized electric field would also lead to a better fiber formation. So in order to investigate this, we changed the polarity of the collector within the setup because usually the collector is charged positively, so we studied a negative polarity of the collector and the final fiber diameter. And we achieved a significant reduction in diameter and also a very dense and homogeneous nonwoven. We also performed the first test on our pilot scale machine and found out that this strategy works for both machines, so the lab scale and the pilot scale machine. So yes, let's conclude this question also with a clear yes. A negative collector leads to fine fibers and a uniform nonwoven. But as you can imagine from the name lab scale machine and single nozzle machine, the final size of our nonwoven is limited. So in order to prepare a filter layer for a medical face mask, we need a larger machine, which brings me to our pilot scale Melt-Electrospinning machine. So this machine has 600 nozzles. It uses an extruder and a conveyor belt, which technically allows the continuous production of a nonwoven. And it is the largest machine worldwide of its size, which has its place at the Maastricht Institute for Biobased Materials. And as you can imagine, if friends would come over and you need to prepare a large amount of mashed potato, we need a large sample size for a filter. So at the end on this machine, we were able to, or I was able to make a filter layer for a face mask, which you can see on the picture, and to use this as a filter. And however, the transformation from the lab scale machine to the pilot scale machine was challenging, because at the end, we did not really achieve a homogeneous sample which stick together. So we needed to make use of a post-processing method. However, at the end, we achieved fibers with a diameter of 1.7 micrometers. And we were able to develop 3 prototype masks. But, as I said, the transformation is challenging. So now, coming back to the initial question, is it possible to produce a Melt-Electrospun filter for medical face masks from bio-based and biodegradable PBS? So yes, in lab scale, we were able to achieve nonwovens which have a low diameter, which also had antibacterial characteristics. In pilot scale, we were coming closely to the 1 micrometer fiber, which is smaller than the fibers used in the conventional face mask as of now. And we were able to develop 3 prototypes. However, we definitely need further machine optimization in future to also optimize our filters. And we are very far away from an industrial process yet. So let me answer this question for now with a not yet. However, other than a chef not sharing the secret behind the recipe, today I would like to share my secret of my recipe, which is, in order to prepare such a filter which I made, you need to use 235 degrees of temperature, 40 kilovolts, a spin pump speed of 2, a distance of 5.5 centimeters, and at the end it will lead you to a uniform nonwoven with a diameter size of 1.7 microns. And yes, this is maybe not the recipe of a full success for now, but maybe in future we can make it to a recipe of success. And this being said, these are my references. And thank you for your attention. And I would like to give the word back to the prorector.
Thank you very much for your timely presentation. Before we proceed with the opposition, let me briefly introduce this committee to the audience. On my opposite left, we have Professor Zijde and Professor Groten, which are the thesis supervisors, and they are followed by Dr. Dolmans. And on this side, we have Professor Jokkenheuvel, and next to me is Professor Honing, who is the acting secretary of the degree committee. And our committee is completed online by the participation of Professor Hopman and Professor Meyer, whom are visible on the screen. And finally, my name is Thuisman. I'm representing our rector for this meeting. And now I hope you also enjoy the continuation of this session. The opposition will be opened by Professor Jokkenheuvel, who is the professor of biohybrid and medical textiles at our Aachen Maastricht Institute for Biobased Materials, and he's also the chair of the assessment committee. Professor Jokkenheuvel, the floor is yours.
Thank you very much, Chairman. Dear candidate, first of all, thank you very much for this nice thesis. It was really a joy to read it and to learn a lot. You are now the expert here in the field, so let's look to dive a little bit deeper. So you're talking about melt-electrospinning. Most people are doing solution electrospinning. So can you a little bit elaborate about what are the differences? Why are what difference we have with parameters? What's the pros and cons of both sides? Yeah. And where are, at last but not least, the limitations of both methods?
Yes. Highly esteemed opponent, thank you very much for your question, which is indeed a very important question to consider. So, as I said, there are 2 different methods. So one is solution electrospinning, one is Melt-Electrospinning. Solution electrospinning was, let's call it, born first. So solution electrospinning considers, or it requires the prior solving of a polymer in a solution. So, and this makes the main difference, because in Melt-Electrospinning we process the melt directly, whereas in solution electrospinning it requires the prior choose of a solution. The method itself and the fiber formation process is basically the same. So both consider a solution, a syringe, which either contains a solution or a melt. We have a nozzle, and then we establish the electric field between the nozzle, the tip of the nozzle, and the collector. So I would say the fiber formation process is the same. But, however, there are major differences which come from the solution and the melt. Because since we solve the polymer granules in a solution, we usually have a very higher conductivity and a lower viscosity in terms of the melt, which has a benefit for certain applications, but it can also have a disadvantage. Whenever we want to use those products at the end for biomedical applications, for instance, there would be a risk of transferring some toxic ingredients to the final product, whereas in Melt-Electrospinning this is not the case. And also that we don't need to use toxic solvents could bring us to a more environmentally friendly.
You always need toxic solvents?
What was that?
Do you always need toxic solvents?
No, you don't. I think there is also a lot of research and alternatives now looking for more environmentally friendly solvents. However, there's one thing which doesn't change, and at the end you dissolve a few grams of polymer in a solution, and during the process you have a lot of evaporation. So at the end you lose a lot of solvent, and it gives you a little bit of, let's say, a non-woven structure, whereas in Melt-Electrospinning, you process the granules, and at the end, you get what you've put in. So
that's very interesting. So you said that the most important parameter in Melt-Electrospinning is the electric voltage, right? Is it the same in solution electrospinning? Or what do you think is the most critical parameters?
So in general, we have certain parameters, and all parameters need to be adjusted rightly for the material that you're processing. So I would say in my case, I made the experience that for PBS and Melt-Electrospinning, the electric field strength had the highest influence. However, I think you cannot just simplify that. And also for solution electrospinning, I think you really need to find that out for each material. But of course, there's also the flow rate, which has a very high influence on the final formation. And also the solvent that you use, because the solvent needs to be adjusted to the polarity of the collector at the end, so it needs to interact.
Yes, and you have a lot of disturbance factors in solution electrospinning, which you don't have in the Melt-Electrospinning, which give you, I think, at the end, a more stable process, like humidity, temperature, which is a really critical thing. It can lead to complete different fibers. Yeah, thank you very much. I have a little bit time left, so you know I'm a physician, I'm a cardiothoracic surgeon, so I'm of course interested in your medical application, not only as mouth master, but what you all can do with these kind of materials and with non-wovens. So biofunctionalization is something you have done, by the way, as an add-on effect to your additive. With the silver ions, for example. How do you think you can, at the end, further make a biofunctional network, perhaps for other applications like wound dressing or even for implants with your technology?
So, in general, curcumin, for instance, is known to be pH sensitive and light sensitive, which could probably bring us very beneficial characteristics, or could be very beneficial, for instance, for wound dressings. If we would use a curcumin wound dressing and we can observe the changes in color depending on the pH values of your wound, as well as the sunlight, then maybe it can help you a bit with finding out how your wound is developing. But also I think, I think there could be also ways in order to make, or in order to integrate additives that maybe release some drugs, for instance, to make drug-loading fibers.
That's the question: which kind of additive you can add. So don't think about the drugs or additives you can put in. But if I think about solution electrospinning, for example, I can make with high humidity, I can make porous fibers. You think about how can you enhance or how can you functionalize your textiles? What possibilities you have in mind? Perhaps as post-processing, perhaps within this process, so always nicer, do it in a one-step process. But do you have some ideas?
I mean, coating is always an idea. You can always add certain coatings that you need for your application, but I think this really depends at the end on the application and the intended use. But in general, I think the nonwovens made from Melt-Electrospinning have a very high surface area. So I think if you would like to use it for any wound dressings or biomedical applications, I think from coating you can use whatever coating gives you at the end your characteristics that you wish.
And they do the coating within your process? Is that thinkable?
I mean, within my process, well, by adding certain additives.
No, without additives. Really coating.
Okay. Well, that's a very interesting question. I didn't think about this because I think this was not the scope of my research. But
of course not.
To be honest, I don't know how to code that within the process. Perhaps
coaxial spinning could be a possibility for that. I have still time, or should I? So I come to the last, and perhaps I may ask a Paranymph to read the proposition number 5.
The proposition number 5. A biodegradable material is not always the best option compared to a conventional material. It should be chosen wisely depending on the intended use.
Very wise words.
I hope someone is going to ask about this.
Yeah, but this proposition, can you elaborate with regard to your project? What do you think often the PhD candidate is more wise at the end of the thesis? Yeah. What do you think? And could you elaborate a little bit on that?
Yeah. So at this point, I would like to make clear that the initial idea was never to make a filter which is biodegradable, which is biodegradable, but which you can just throw in the environment. Like a biodegradable material or a biodegradable product should never open the floor to just be thrown into the environment, which is, I think, and what I learned during my research, something that a lot of people believe. And also, so biodegradability makes sense for me in 2 scenarios. So one is if you have a high abrasive material or a material which emits a lot of microplastics into the environment. And also, since the face mask would be very close to the mouth, I know there are studies by now that say that microplastics is also found in the human body and even in the brain. So this could be maybe a way of, if you have a biodegradable filter or the nanoparticles would at the end, I don't know, degrade, that could be beneficial and a good idea. And also a second approach is that biodegradability makes sense, for instance, for materials or products that include organic substances, for instance, a tea bag or something. But just because you use a biodegradable or bio-based material does not mean that it's going to be environmentally friendly. And those things really need to be elaborated with specific tools. For instance, using life cycle analysis or something to really study if a material would make sense to be made from bio-based and biodegradable materials.
Thank you very much. We can make a debate overnight about that. Thanks a lot.
Thank you very much. The opposition will now be continued online by Professor Hopman. Professor Hopman is Professor of Plastics Processing at the Institute for Plastics Processing at the RWTH Aachen, and he's a member of the Assessment Committee. Professor Hopman.
Thank you very much. Good afternoon, dear candidate. Thank you very much for your presentation and also for the thesis. I really enjoyed reading the thesis, and I really enjoyed very much the very holistic view on the process and on the material, which is important to come to a product and a more sustainable solution for a product like that. So thank you for that. However, I have a couple of small questions. I would like to first look on the basic process, the formation of the strand. You explained also in your presentation that the formation of the Taylor cone is very important for the electrospinning process. But if you press a polymer melt through a nozzle, usually you get a strand which looks very different from what you need from the Taylor cone. Maybe would you please describe a little bit what is usually the shape of this strand, and how can you now create the Taylor cone by the different process and material parameters like temperature, volume flow, molecular weight, and stuff like that. Could you elaborate on that a little bit?
Highly esteemed opponent, thank you very much for your question. So usually if you would just melt the polymer in the syringe and you would just press it, you would see the formation of a drop. So you would just see the formation of a drop and not the formation of a Taylor cone. The Taylor cone is something which is typical for the electrospinning process. And this is formed by the electrostatic repulsion of the field exceeding the surface tension of the material. And in order to do so, you need to have a strong electric field. So whenever the electric field strength is higher than the surface, and the surface tension of the material can't hold it anymore, then you see the formation of this so-called Taylor cone. And what I found out from my first study is that the electric field strength in terms of PBS has the highest influencing, or is the highest influencing parameter on the final fiber formation, which doesn't mean that the other parameters that we're using are not also important. So that's why the Melt-Electrospinning process is a high complex process, and it requires a balance out of all the parameters. So we need to have a sufficient flow rate, because also the flow rate needs to be adjusted according to the field strength. Whenever you have a lot of material and a high mass flowing, you need a higher electric field strength than in terms of a low flow rate. But also the distance from the collector and the nozzle needs to be evaluated, because if you have a short distance, it gives the fiber a limited time to interact with the electric field, to form the Taylor cone formation, to have the whipping and these instabilities, which are crucial for the process. So yes, to answer your question, so all the parameters are important, and those need to be adjusted in order to really make sure we have the formation of the Taylor cone at the end.
Thank you. You didn't mention the rheology, the viscosity of material right now, but in your thesis you spent a lot of efforts to investigate the rheology and the viscosity performance and the impact of shear rate, temperature, molecular weight. And I would like to draw your attention on the question of the impact of the molecular weight to the rheology and the formation of the Taylor cone, which is obviously very important. And the molecular weight and its distribution. I think that is something you could maybe comment a little bit more.
So, there is a difference in flowing of a material which has very short chains and very long chains. So we would like to have, for the Melt-Electrospinning process, we want to have a narrow PDI, so bringing us to equal distribution of the chains, and also when we have a high molecular weight, usually we have a very high viscosity, which hinders just the flowing of the material. And as I tried to explain during my presentation, if we have a very high viscous material, it's very hard to stretch. So I always like to explain the example of water and honey. So if you can imagine, water just flows very quickly, which is also something that we don't want, but also we don't want to have a honey-like material which hinders our stretching, which comes from very high molecular weight polymers. So it's always important to have a balance and to have a molecular weight or a viscosity which is high enough to form a fiber, but it should also be as low as possible in order to enhance our interaction with the electric fields.
Okay, thank you. Maybe we switch to a different topic. A few minutes left. You analyzed also the process of electromelt spinning very nicely and intensely, and you made this ANOVA analysis. And it came out that the electric field strength is very important, which you already described, and the throughput, of course, and also the nozzle to collector distance. But it was a little bit surprising to me that the temperature actually did not have any impact on the fiber diameter. What is the reason for this surprising effect?
So the reason for this is that prior to the spinning, we did a very intense analysis of the material. So before we started the spinning process, I had a look at the conductivity of PBS at different temperatures, the viscosity of the material at different temperatures. That's why I only chose at the end to process the material at 2 temperatures. So I think that this could maybe also leads to a reflection that at the end I only studied 2 temperatures which are actually quite close to each other. So I investigated 235 degrees and 265 degrees. I could imagine that if I would have tested maybe 2 temperatures which have a very high difference, for instance 100 and 250 degrees, then we would see a total different curve there and also a higher impact. But I think just because the statistical analysis now doesn't prove it to be a very important characteristic parameter, it should still be considered to be very relevant for the process.
Okay, yeah, I think that's a very important because one is to assess the process and the other one is to understand the process, and for that the temperature still needs to be included and to be assessed in the analysis. That's for sure correct. Yeah. Maybe one short last question, if I'm allowed. Otherwise, somebody else.
Yes, you're allowed.
Okay, thank you. You also made this analysis about the cost of the product compared to the currently used polypropylene, which is of course very important when you think of a real application. And when we look on the material, there's of course the cost of the material itself, but there's also the energy input, which is very much linked to the material and the properties of the material. What is the most important characteristics of the material defining the amount of energy which is needed to process the material?
So I always compared my process to the conventional medical face mask and the filter, which is made from PP. And there is one major difference, and PP doesn't need to be dried before we spin it and before we process it. Other than PBS, which is a polyester, which takes up a lot of water because it's a polycondensate, we need to dry the material up front the processing. So I think this should reflect also in the energy usage at the end, because this is a large difference that one of the materials needs to be dried before the processing and the other one doesn't need to be dried.
Absolutely. That's a very important factor. And of course, also the processing temperature is different, which is important. And also the melt entropy might be different. So the energy is important, not just for cost reasons, but also for, let's say, sustainability reasons to be included. Okay, thank you very much for the moment.
Thank you. The opposition will be continued by Dr. Dolmans, who is a technology manager at Oerlikon Man-Made Fibers, and he is also a member of the assessment committee. Please switch on your microphone. Yes, thank you.
Thank you very much. Thank you, dear candidate, for your thesis. I really enjoyed reading it, especially the part on the rheology studies that you did. I'm a rheology fan. And in that direction also, I would like to discuss or question some parts. I would kindly ask one of the paranymphs to open page 92, if it's possible. And then to, that's figure 313. Yeah, that's where you show a rheogram on the viscosity over time. And I'm not so much interested in the additivated ones, but on the PBS. Yeah. You can imagine. You also give an explanation on this. Maybe you can elaborate a little bit first on the curve and the increase on the PBS.
Yeah, sure. So, hi, esteemed opponent, thank you very much for your question. Yes, I would like to elaborate on this curve. So what you can see is the complex viscosity of the material over time. And what we can clearly see is on the left side we see the curcumin additives and the PBS, and on the right side we see the silver and the PBS. So I would like to start with the one on the left side, where we can see that for curcumin we have a clear reduction in viscosity, whereas for PBS it is first stable and then we have a clear increase in viscosity. And potential reasons could be that I believe, like one reason could always be cross-linking, what I also described within the thesis. But I think there's also another potential reason, which could be further polymerization over time, where I think that during the viscosity measurements, the material just further polymerizes at this temperature, whereas the curcumin additives just lead to a reduction in viscosity because they are very small molecules which disturb the polymer matrix, leading to a reduction. And the same we experience with silver. So there we also experience the uptake of viscosity.
Okay, I'm glad you overthought that one, because you mentioned 45 minutes of residence time. Yeah. And cross-linking would really be a harm in that process then. So, yeah. If I got that correct at least. Yeah. So can you maybe think of an experiment, or maybe on the data that you have on this experiment, on a way to find out if cross-linking has found place or an increase? Can you explain that?
Yes. So one experiment that I could have done, which I didn't do, but which could be done in future, is to try to solve at the end this PBS in a solvent, for instance, HFRP. Or another solvent, because highly cross-linked or cross-linked materials, they don't dissolve in those solvents, whereas materials which are not cross-linked, they should dissolve. So this could be an indication to find out if the material is cross-linked or not.
Okay, and with the data on hand, I mean the raw data in this experiment?
Well.
Okay, it's a tricky one, but you can look at the storage module and the loss module, and there is a crossover. When it happens to cross-linking, it's a Tanga delta, and that should be already at hand in that data. Thank you very much. I still have one. Yeah, I still have time for a proposition. You proposed here. Maybe someone can read it also. Number 7, please.
Proposition number 7. There are good reasons for doing TGA measurements before spinning trials. Keep that in mind.
That's a good one, yeah. But maybe you can elaborate on that a little bit. What is your mind behind it? I will counter-propose. We are mostly processing way below that temperature on TGA.
Yeah. So, in general, TGA is a measurement which we use to find out the degradation temperature and also the temperatures at which 5 or 50% degradation takes place, which I used because I have two different machines. So the lab scale machine, where the material is 2 minutes in the syringe and then it's ejected, and then we have the fiber formation. Whereas for the pilot scale machine, we have a much higher dwell time in the machine. But the first trials, initially, when I just tested the material, I didn't really take those results by heart, and I filled the syringe, and I found out that material was just degraded and black, and so I found out that, or I learned that it's a wise decision to do TGA measurements before you start the processing, in order to not waste time and not waste material, and to,
Okay. Thank you. Thank you.
The opposition will now be continued by Professor Honing, who is a professor of analytics and system imaging at M4I at Maastricht University, and he's also a member of the assessment committee. Professor Honing.
Thank you, Mr. Prorector. Dear candidate, first of all, congratulations with a beautiful search of new technologies and the feasibility limitations on that. And of course, there's a lot of questions always. And as a scientist, I think we also should speak about definitions and to keep in mind that we all speak about the same. And you start in page 12 or 13 to speak about recycling of the mouth caps, which was not really able because of hazardous microbes within the context of COVID. But what are microbes for you? What's the definition of microbes?
Highly esteemed opponent, thank you very much for your question. Yes, so...
Maybe I help you. Microbes are tiny living things, but COVID was about what?
A virus.
That's not a living thing.
Yeah.
So it's not a microbe.
Yes, but filters or face masks or filters in general can also, like, they not only be used to filter viruses or bacteria, so they could.
No, I fully agree, because that is also maybe a nice discussion, because the mouth caps you discuss here in your thesis are what we call surgeon mouth caps. So actually it's to protect the patient from what is coming out of the mouth of a surgeon and not of corona, and I completely agree for the applications. But in reality, of course, the mouth caps, which was called FP2, the very heavy ones, they were protecting us against the virus, and maybe that's also a good question to that. But okay, perfect. I think it's clear that these mouth caps were used, actually maybe misused, because we did not want the FP2s, because you cannot breathe in that, and that's why all the people had problems. Okay, thank you. Especially people with asthma will not use FP2, of course. Next to that, and that's maybe also on definition, what do you think is a biopolymer? Because I'm a little bit, I'm come also from the health science, and biopolymers for me are proteins and peptides.
So for me, a biopolymer is a polymer that can be derived entirely from bio-based resources. For instance, from sugars or from the fermentation, but there are also
But
plants.
Oil is coming also from plants. Why is that not bio-based?
What was that?
Oil is also degradation of sugars and furane from plants and human. So why is oil not bio-based? It's even degraded more. I mean, no, it's just a discussion. I think on bio-based is for later on. But I think it's always good to really discuss within scientists about what words mean. And for me, a biopolymer is a peptide. And then I think you were speaking about that on the microplastics, biodegradation, that's the same word, because I think what you are saying is biodegradation is the formation of microplastics, and that is a physical process. Or what is biodegradation for you?
Well, I think there are certain ways of biodegradation. So there's, for instance, industrial composting, which is a way of degradation. There is home compostable materials, which also refer to biodegradable materials. So for my application, I focused on a material that could bring us a benefit in terms of having microplastic which degrades, for sure.
Okay. But I think what is misunderstood, and maybe you can ask maybe one day the people in India about biodegradation of soaps and other polymers in their big rivers, because biodegradation is also degradation by bacteria and photo-induced degradation. And then the big problem is that we get huge amount of very toxic monomers which are released from these biopolymers. So I think the microplastics is maybe a problem, but the release of monomers which are highly toxic can be even more. And related to that. No, that was on definitions. Again, on electrospinning, I think it's very interesting because actually I use everyday electro spraying, where we use electrical field to spray solutions to evaporate molecules out of the solution into a mass spec. And you say the strength of the field, and I think it was already elaborated on by the previous members of the committee. You mentioned then the flow rate and especially the Taylor cone. And the Taylor cone is highly linked to this, let's say, surface tension of the material, leading to droplets in the end. But why are there no droplets formed in this polymer then?
There are no droplets formed because the repulsion of the electric field is higher than the surface tension of the material.
But in solvents it will lead to droplets.
What was that?
In solvents it will lead to droplets which evaporate and then you get evaporation.
Yeah.
So there's in this transition something going on.
Yes. Well, I did not consider solution electrospinning, so I could imagine that the interaction or the solvents, they are just more interacted or more attached or attracted to the field, that they more quickly form the Taylor cone.
So we agree that actually your statement of proposition number 1 already explains that number 2 is not completely true. Yeah, because you say it's very tiny optimization of a lot of factors, and that only the strength, of course, is not maybe important in your case, but also they are not linearly dependent on each other. Mm-hmm. And that makes it extremely difficult. That's why I think it's so interesting. About sustainability, maybe I can have some questions. In chapter 3, you suddenly add silver to your mouth mask. And of course, silver is known to a certain extent to have an antimicrobial activity. But then I started to calculate, because effectively, if you look to page 84, and when, so the E. coli is not really a problem because you can swim in the river in Paris and not die of E. coli. But Staphylococcus aureus is really a problem, and you need to load something like 15 or actually 20 milligram per milliliter. Mm-hmm. Now I calculated something like 40 milligram per mouth mask times 2 billion of mouth masks, that is about 100 tons of silver. Do you think that's sustainable?
For sure not. Well, I think the scope for me was to evaluate if, like, the main scope was to evaluate if those additives are reducing my viscosity and increasing my conductivity, which was, and as I mentioned before, this was a side effect which we found out, but the initial plan was never to fully load those fibers or face masks with silver or curcumin.
Luckily,
so,
but then still it's a lot.
Yes, still it's a lot. Yes, so I wouldn't consider this to be sustainable.
No, because you were speaking about toxic solvents and then suddenly about silver. You have one question still?
Okay, if you have a pressing one.
A very small question. I think it's on page 52. And I was a little puzzled. I'm an analytical chemist, so I'm looking to analytical data. I see a mass molecular mass distribution, most probably done with size exclusion chromatography. And when I look to 235 and 265, they are the same. But I see a completely different polydispersity. The polydispersity is more or less the same, but the mean molecular weights and molecular masses are completely different. So what's going on here? Because it's not apparent from the SEC picture. And even from the SEC picture, I don't understand why there's so big difference also in the molecular weight for the granulates. So the dispersity is not too different, only the mean is very different.
Yeah, I see.
Yeah, strange data. We will discuss afterwards. Thank you very much.
Okay. We continue the opposition online with Professor Meyer, who is a professor of photonics and material science at the Hochschule Hamm-Lippstadt. Professor Meyer.
Yeah, thank you. Thank you for the nice presentation, dear candidate. Of course, I too have a couple of questions, and I want to link to the questions regarding sustainability. I was asking myself, is there really no option for the reuse of face masks? So none at all? Do they always need to be discarded as such?
Esteemed opponent, thank you very much for your question. So, of course, there could also be other options than just throwing the face mask away. So, I mean, if there would be a way of identifying face masks that are contaminated or face masks that are not contaminated, maybe those face masks that are not contaminated would at the end could be collected in a way and then recycled, because PP is a material which can be very well recycled and which leads again to very good properties. So maybe this could be a way finding out or identifying masks and filters that are actually contaminated and some that are not contaminated, to at the end have a sorting and a recycling of those.
Yeah, okay. Let's assume we have a way. Do you think there's a difference in the performance of PP and PBS with respect to reuse? So is one more advantageous than the other, and would this lead to a new assessment of the sustainability of one or the other?
May I ask you to rephrase the question? Sorry, I think the
audio
is a bit...
Not a problem. I'll do my best. So the question is, if we had a way to reuse the masks, so assuming the sorting and everything is in place, and then we look at the materials you were discussing in your thesis, polypropylene and PBS. Is there then a different assessment of the two materials with respect to the reusability of the masks in the end? So would this turn the favor maybe on PP as a more sustainable material if you reuse the mask? Something like that would be my question in the end.
So I hope I got your question right, but I would say if we recycle PP usually brings us very good mechanical properties even after recycling. So, but in terms of PBS, which is a biodegradable material and which is a polycondensate, I could imagine that over time PBS loses some of its important characteristics. So I would assume that if we recycle PBS at the end, then it wouldn't bring us to the same properties than we would get for PP. If this was the answer to your question.
Yeah, Thank you. I have another question entirely, so I'm back to the processing. So if we look, you were referring to the problem that for the bigger machine with the 600 nozzles, that you don't get a non-woven, but you get a agglomerate of non-fused fibers. And this was related to the limited temperature and also limited temperature uniformity at the nozzles. And I got the idea from the idea that was already in your work to heat the final fleece with a, for example, IR source, that you might also try to heat maybe the Taylor cone or whatever is protruding from the nozzle, for example, by a laser beam or something. So very directly put the heat where it's needed, and maybe by this come to a uniformly heated, over all 600 nozzles, uniformly heated PBS strands. What do you think about this idea? Do you think that's by any means feasible, and what kind of radiation would you use?
This is a very important question. Also out of the perspective that if we could integrate this option which you discussed, we would not need to rebuild an entire machine. And I tried to do something similar by adding the infrared heater. Because the most important thing that you need to consider is, in order to have the stretching of the fibers, the temperature needs to be higher than the crystallization temperature. So what I experienced is that the temperature below the nozzles was lower than the crystallization temperature of my PBS, which led to the early solidifying of the material. So whenever you try to prepare such, let's say, such a method or such an optimization, this is something very important to consider, and also to stick in between the recrystallization temperature but below the melting temperature for sure, because what we used was we had the infrared heater with I think 250 degrees or something, but our my PBS has a melt temperature of 210, so that's why we saw the formation of those droplets. So this is something which is very very important to consider, but yeah, this can maybe be evaluated in the future.
Mm. Did you look at the absorption characteristics of the PBS? So you can make a proposition what kind of source you can use to heat the material, which wavelengths it should have?
What was the question? Which source of heat I can use to?
Yeah, if you record an absorption spectrum of the PBS, you will be able to see where you can heat it up effectively by radiation. This is what my question leads to. Do you have an idea what kind of radiation you could use? Is it IR? Is it maybe UV? Is not really a good idea because it will also degrade the polymer. But can you make a proposition? So is IR, you used IR, is it really good way to heat it up? And if IR is that's a broad range in the spectrum. So do you have an idea?
Well,
but maybe also for later to discuss.
Yeah. But I think the most important thing is just to always stay below the melting temperature. But PBS is, since PBS has its TG in the minus area, it's already flexible also at room temperature, which is also...
Maike-Elisa Ostheller, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and our return in this room.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
south side. 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. On the line, I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. The mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. To the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. Long road to the south side, 10 miles in my rearview mirror, I know what it felt like. My goal's only getting clearer, east side to the west side. No place like home, if it's questions that you've got, go the extra mile and that. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
Maike-Elisa Ostheller, the degree committee here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Zijde is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here I hereby confer upon you, Maike-Elisa Ostheller, the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with a degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university.
Professor Zijde will now read the laudation.
Dear Maike, with your dissertation you have made an important contribution to the further development of Melt-Electrospinning and our group. During your doctorate, in addition to electrospinning, you worked on the Glaukos project, as we all know, to develop fishing nets and textiles that are degradable in seawater. However, the topic of electrospinning was so important to you that you also wanted to explore this field and did the job you presented. On the basis of your work, a new project has been acquired. Others are submitted as proposals. Your work attracted several companies and led to various smaller industry projects in this field of electrospinning. You leave a well-tilled field. But how did you actually come to us? I was looking 4 years ago for doctoral students, and Robert Groten recommended you with very laudatory words, so really convincing. And when I met you for the first time, I knew that is the right person. Positive mindset, hands-on, knowing textiles, so that was what we were searching for. And I was pleased that Robert supported the supervision and is here today as the second supervisor. Thank you, Robert. For our group, you were always an important source for inspiration and leisure activities. For the group, as you planned many things, and I have a weak point there, so thank you for all these activities. And as we learned, you're cooking a lot, and as a passionate foodie, you always had a sure hand when it came to organizing events and parties with the group, so thanks again for that. We would have liked to keep you with us after your doctorate, but as your family is at Stuttgart, unfortunately, I must say, there's no chance to us to defend that and to make you staying here. On the top of that, you have accepted a great job as a consultant in the field of sustainability right there. Obviously, too many good arguments, and you have to go there. We wish you continued success for the future and everything else you wish for. Thank you for your time with us. Be sure you will be missed by me and the group.
Thank you. Thank you.
Dear Dr. Ostheller, also on behalf of Maastricht University, I congratulate you with the doctorate degree that you've just required. Now, before I close this meeting, I would like to thank all members of the degree committee and especially those coming from far. Your participation is much appreciated. And before we close the internet connection, let me offer our online members the opportunity to congratulate our candidate. Professor Hopman, maybe you can go first.
Dr. Ostheller, congratulations with the successful exam you had today. I'm really happy to be part of this ceremony, but also I've been happy to read your thesis and to listen to your presentation, also to have a discussion with you. As you worked out very nicely, it's clear that sustainability is a huge challenge, but also we have to investigate the details. You did investigate a lot of the necessary details, and for that you opened the room for a number of questions. We could just tackle some of them, but that was a really huge step for electrospinning, Melt-Electrospinning. So thank you very much for your scientific approach, for your scientific work you did, and all the best for your future. Congratulations for the PhD, Dr. Ostheller.
Thank you.
Then we move to Professor Meyer.
Yeah, I will keep it short. Dear Maike, congratulations to your successful defense and also to the thesis, and more success, even more success in your new job.
Thank you.
And a nice celebration afterwards now. I hope this starts soon, and I don't want to hamper it by talking too much. So everybody have a nice celebration.
Okay. Before closing this meeting, I'd like to say a few words on the further order. We will now first use the opportunity to take some pictures with the candidate and the full degree committee, including our online members in this room. And after that, we'll take some more pictures at the stairs in the main hall. And if I understood correctly, the audience can walk to the nearby restaurant Kipasa to congratulate Maike-Elisa. And once again, I'd like to thank you all very much for attending this milestone event. And I now close this academic meeting.
Recording stopped.
Alles Gute dir.